Uh, Welcome PCS members and our friends to our today's Tuesday PCS IBS seminar. It is a great pleasure to have with us Professor Jae Dong Noh from University of Seoul. And I would like to invite our scientific host, Dario, to introduce our speaker. Please, Dario.
Okay, thanks, Dylan. Yeah, it's a great pleasure to have Jae Dong today as our speaker. I mean, I was hoping to invite him in person, but the fourth wave of Corona made, let's say, preferable to go online. So let me introduce our speaker. So Jae Dong got his PhD in Seoul National University in 1997. After that, he was a postdoc in several places, like in Germany, then in Hina University, Seoul National University, University of Washington. And after that, he started to be a professor, first in Chungnam National University, and then he moved to University of Seoul, where he's now a full professor. Now, his research interests are mostly related to the physics of thermalization, I would say, in quantum many-body systems. And related to that, today's talk will be about operator growth dynamics in the integrable and non-integrable Ising spin chain. Jae Dong, please, you can start.
Okay, thank you very much for the kind introduction. So this is my title. So today I'd like to, talk about the operator growth dynamics in the Ising spin chain. And actually, this is my new research project. So I began to study this topic very recently. And this presentation will be the summary of my recent preprint. The number is here. Okay, so any comment and suggestion will be welcomed. And if you have any question, please feel free to ask during my talk. Okay, so quantum summarization deals with the question whether an isolated quantum system eventually thermalizes or not thermalizes through their unitary time evolution. So there are many aspects of this quantum thermalization. So actually, there are many criterion or ingredient for the study of this quantum thermalization. For example, in the context of solvability, the thermal system is believed to be non-integrable, while the non-thermal system is believed to be integrable. Okay, and you can check. You can approach this problem in terms of so-called level spacing, which means that the statistical property of the Hamiltonian eigenvalue, energy, the statistical property of these energy gaps. So it is believed that the thermal system, this level spacing follow the Wigner-Ising distribution, while this integrable and non-thermal system follow the Poisson distributions. And actually, most recently, the most promising criterion is the so-called eigenstate thermalization hypothesis is believed to be the most promising, way to say something about this quantum thermalization. So this ETH is some kind of hypothesis for the matrix element of physical observable in the Hamiltonian eigenstate basis. So there are some very specific prediction for the matrix element. So if this hypothesis is satisfied, then the system eventually thermalizes, and if not, the system does not thermalize. Actually, these directions have been studied for many years, but very recently, some people try to approach this quantum thermalization in terms of complexity. Okay, so let me just briefly give an idea of what this complexity means. Some people study so-called out-of-time ordered correlation. Okay, so out-of-time correlation means some correlation functions of a few or several physical operators, but as you can see here, the OTOC means the correlation function of operator which are not ordered in time. Okay, so actually the physical meaning of this OTOC is can be seen best with this so-called squared commutator. Okay, so if you see this form, so this is the commutator of a local operator V and another local operator W, but W is the operator at time t in the Heisenberg pictures. So if V and W is a local operator, and then at time t equals to 0, then this commutator is just a very local operator. Okay, and if the support of V and W are far apart, then the initial squared commutator vanishes. But if there's a time evolution, then this time-dependent W has a more wide support, so they will this commutator will have some. This commutator will have some more pronounced overlap. So actually, this squared commutator can describe how this operator grows in some extended Hilbert space. So, for example, for some system which is believed to be chaotic, this squared commutator is believed to grow exponentially in time. Okay, so if from this form one can define the so-called Lyapunov exponent in analogy with the classical chaos. So if you measure this squared commutator, and if it grows exponential, then we can say that this system is quantum chaotic. Okay, and very interestingly, Maldacena proved several years ago this Lyapunov exponent has some universal bound, which is determined by the temperature of the quantum system and also the Planck constant h. So in this sense, this Lyapunov exponent has some universal meaning. Okay, so somehow using this squared commutator, one can define quantum chaos. And later, some people suggest, another picture. So let's just focus on the time evolution of the operator itself, not the commutator or not the correlation function. So suppose I have some physical observer, maybe this is just a local operator denoted by this O, okay? Then this operator evolved in time according to this von Neumann equation in the Heisenberg pictures, okay? So as a result of time evolution, this local operator becomes non-local and non-local as time goes during this time evolution, okay? So actually this Parker et al. Proposed some systematic way to characterize the growth of this operator in the extended space, okay? So this operator growth can be regarded as some kind of time evolution in the extended Hilbert space. So that means just regard this operator as some state in some extended Hilbert space. And if you introduce, and one can also introduce the inner product of two operators in this way. For example, the inner product of A and B can be taken in this form. This means that this is the this is the average of A times B with the uniform measure in the Hilbert space. Okay, so in the sense, this can be regarded as infinite temperature average. Of course, you can introduce some finite temperature density operator here to define the different form of inner product, but the simplest one is given by this infinite temperature temperature average. Okay. So once you define this inner product between two operators, and then actually this operator becomes a member of the Hilbert space, but of course this is different from the Hilbert space for the state vector, but this is extended Hilbert space for operator, okay? And this operator state obey this, this is just another form of this von Neumann equation, and this commutator with the Hamiltonian can be seen as the operator in this extended Hilbert space, and usually this is called the Liouvillean superoperator. Okay, so once you have an operator, then the Liouvillean superoperator act in this way. So you just take the commutator with the Hamiltonian. Okay, so let's focus on the time evolution of the operator in the extended Hilbert space. Okay? And so once you start, if the initial state is the local operator, and the time trajectory of this state remains within the so-called Krylov space. Krylov space is spanned by this state. I mean, the initial state and initial state multiplied by this Liouvillean operator, and the initial state multiplied by the Liouvillean operator 2 times and n times. Okay, so every the time, trajectory should remain within this Krylov space, and the dynamics in this Krylov space can be well described by the so-called Krylov basis, and the Krylov basis is constructed by using the so-called Gram-Schmidt orthogonalization process. Okay, so this can be summarized by this simple formula. Suppose you have an initial state. Okay, this will be taken as the first basis state denoted by O0. Okay, and then if you apply the Liouvillean operator to this initial state. Okay, then so you have an initial state here, and if you apply the Liouvillean operator, then it will create some orthogonal component. Okay, and this additional orthogonal component will be assigned to the new basis vector. Okay, and of course there are some component which can be written in as a linear combination of the previously generated the operator. So this can represent the overlap with the previously generated basis vector. Okay, so in this way you can construct the orthogonal basis set for this Krylov space, and this basis states set of basis states is called the Krylov basis. Okay? So actually, this Krylov basis, depends on the choice of this initial state, and also it depends on the choice of the inner product. Okay, so once you have an initial state, and once you have a definition of the inner product, then you will have this Krylov basis and also the matrix representation of this Liouvillean superoperator, time evolution operator. Okay. So actually in the computational physics, this method is just called the Langzhou method. This method, using this method, you can transform any Hermitian matrix in the form of the tri-diagonal form. Okay, so but in this case, due to some specific nature of this Liouvillean operator, the diagonal component is identically 0. Okay, this is very specific case for this operator growth dynamics. Okay? And so all the information of the dynamics is encoded in this coefficient of diagonal coefficient, and this coefficient is called the Langzhou coefficient. Okay, so actually this is something behind in the numerical routines which we use for the matrix diagonalization. Okay, so every information is encoded here, the Langzhou coefficients. So actually, this method has has been widely used in the condensed matter community. For example, suppose you want to calculate some correlation function, autocorrelation function of the operator at time t, at time 0, and operator at time t. Okay, and this autocorrelation function is nothing but the 0,0 component of this Liouvillean operator. Okay, and sometimes you want to calculate some green function of this Liouvillean operator, and actually this green function can be represented in terms of this continued diffraction, and actually the element entering into this continued diffraction is nothing but the Langzhou coefficient. Okay, so in the condensed matter community, this method is referred to as the recursion method, and it has been widely used, especially in order to calculate the approximate form of this green function and also this autocorrelation function. But here, in this operator growth dynamics, we do not want to, we just want to take this method to have some, to access the complexity of the dynamics, not to evaluate numerical evaluation for this autocorrelation function. Okay, and also actually this Langzhou coefficient has a very interesting aspect. For example, we can define this so-called wave function. Okay, so this is the time operated at general time t, and you can think of the component of the nth Kirillov basis of this general, the operator time t. Okay, and so this can be regarded as a wave function in the space of a Kirillov index n. Okay, and because we know the time evolution equation for this operator, and we can also derive the time evolution equation for this wave function phi n, and actually this is the equation of motion for phi n, and this is nothing but the discrete Schrödinger equation or a tight binding model in the semi-infinite train. Semi-infinite means the Kirillov index runs from 0 to plus infinity. Okay, so this is the wave function in the Kirillov Kirillov index, and so from this wave function one can also calculate the average depth. Average depth means the average value of this Kirillov index. So initially, average value is equal to 0, and as a result of time evolution, the system, develop complexity, and they propagate into the deep side of this Kirillov space. So we can expect that this, in general, this average depth should grow as a function of time. Okay, so actually, this type of tight binding model has also been studied for many years because it has some mathematical equivalence to the so-called total lattice, which has long been studied in the classical chaos community. Okay, so up to now, I just briefly introduce the formalism with which one can deal with the operator growth dynamics. Suppose you have once you have a Hamiltonian and once you have this local operator O, and then you apply this recursion method, and then you can calculate this Langzhou coefficient, and Langzhou coefficient determines the time evolution of this, the development of the complexity of the system. The time dependence of the average depth, how the operator grows into the or spreading into the deep side of the operator Hilbert space. And actually, there are a few cases where we can solve this operator growth dynamics. For example, so suppose that this Langevin coefficient is a constant independent of this coordinate n. Okay, then in this case, the autocorrelation function is just given by this Bessel function. So in the long time limit, basically it has some time oscillation with a power law prefactor. Okay, this is just a typical relaxation mode of context matter system. And here one can also solve this discrete Schrödinger equation, and the solution is also given by some combination of Bessel function. And using this, one can solve this the growth in the Hilbert space. Actually, so in this case, this depth one has a linear growth of the depth. The growth is linear in time. Okay. And another case, in another case, one may have the square root of n growth of the Langevin coefficient. Actually, this is realized in some solvable system. And also, if you have this square root n type of growth, then you can solve for this correlation function. This follows the Gaussian form. Okay, and one can also solve this discrete Schrödinger equation. And in this case, the growth of the Hilbert depth is follow the. It grows faster than the previous case. It grows as a squared time squared. Okay, so much faster growth. Okay, and the third case, in this case, the Langevin coefficient can grow linearly in n. For large n, this form can be approximated as alpha times n. Okay, so this is basically the linear growth of Langevin coefficient. And in this case, one can also solve for the correlation function and this discrete Schrödinger equation. And in this case, the Hilbert depth grows exponentially in time. Okay, so actually this is a really chaotic growth in the operator space. Okay, so these three cases are known cases, and actually one can find some microscopic example of these three type of scaling behavior. For example, if you think of a transverse field Ising chain, which is known to be solvable, actually, basically, this is equivalent to the free-formula system. So if you have a transverse field Ising model, then you can apply the Wigner-Jordan transformation to get the free electron system. Okay, so basically, for the free case, some operator follows this type. They just display this type 1 behavior, this Langevin coefficient. There are a little small oscillation, but overall they approach to a constant value. Okay, so the type 1 behavior is realized in the transverse field Ising chain, and also the type 2 behavior is realized in the XXG chain. XXG chain is also solvable, and XXG chain is solvable, but this is an interacting case. Okay, so in this case, for some operator, we have this square root type increase of this Langevin coefficient, and the third case, the chaotic case, is realized by the such that EHTF model. And this model can be solved exactly for the large component limit, and actually this form comes from the large component limit. Okay. So actually, up to now, we just define the way
Sorry,
to...
Jae Dong,
Okay.
Just a simple curiosity. About SYK, you say that this formula is for large Q. Is for large Q, you say, this analytical formula?
Yes.
I see. Instead, for finite Q, the answer is not, I mean, is not analytically no, right?
Yeah, as far as I understand it, this analytic form is known only for Q goes to infinite limit.
Okay.
And there is some numerical work. Numerics also support this kind of scaling law, but there is no closed form solution.
Okay, thanks.
Mm-hmm. Okay, so up to now, I introduced the operator growth dynamics in terms of this Langevin coefficient, and I also listed some known cases. Okay, and now I will explain the geometric bound for this Langevin coefficient. Actually, this bound was found by these people, Parker et al. And they consider some local Hamiltonian, okay, local interaction. So the Hamiltonian is just given by the spatial sum of local operator, okay. Okay, then for this local interaction case, and okay, so just look at this diagram. This is a space, okay, one-dimensional or two-dimensional. So now, once you have some initial operator denoted by this W, okay, then if you apply this Liouvillean operator to this local operator W, okay, then because this Hamiltonian is have two-body or three-body interaction, and if the Hamiltonian include two-body interaction of these two particles, okay, then the result of this Liouvillean applied to W should include some operator of defined on this side and that side. And also, if the Hamiltonian has an interaction involving these two sides, okay, then the resulting operator, the support of the resulting operator should involve these three sides. Okay, and if you apply the Liouvillean operator once more, then the support of the resulting operator should, include this 5 state and 7 state and so on. Okay, so in general dimension, as you apply this Liouvillean operator, then support of the operator is naturally growing. Okay, and by counting the number of supporting site as a function of time, actually they can derive some maximum bound of this Langevin coefficient. Okay, so actually this Langevin coefficient should not be greater than the linear form. Okay, so actually this is the maximum bound. Okay, due to the geometric bound. If you start from some d-dimensional space and the Hamiltonian involve only local interaction, okay, then this is the maximum bound. That's the proof of this Parker et al. But if you consider the one dimension has a very specific, specific property, because the growth of the support is quite limited. Okay, for example, as you can see here, the growth of the support happens only at the boundary of this already existing support. Okay, so in this sense, the growth of the support is quite limited, and if you take account of this special property of the one-dimensional lattice, then you show that there is additional log and correction terms for one-dimensional system. Okay, so these are the maximum possible growth of the Langevin coefficient. Whether the system is thermal or not non-thermal, it doesn't matter. This is just due to the geometrical, from the geometry of underlying lattice. Okay, so once they show this maximum growth, actually this Parker et al. Put forward this kind of hypothesis. So their hypothesis is that the quantum chaos means the maximum growth of the Langevin coefficient, or the maximum operator growth of in the extended Hilbert space. Actually, this is the hypothesis. Okay, so that means for a specific model, if you calculate this Langevin coefficient, and if you get this linear growth of this Langevin coefficient, and then the hypothesis means, oh, this, I can say that this system should be thermalized, okay, or this system is maximally complex. Okay? Of course, if your system is a one-dimensional system, then this is the maximum possible growth of the Langevin coefficient. Okay, and as a support of this claim, and they just show the result of the SYK model. SYK model is believed to be thermal, I mean complex systems, and actually the Langevin coefficient for this SYK model has this form, the linear growth in the larger n limit. And also they did some numerics using the XXG chain or transverse field Ising chain. Okay, so as a function of n, they numerically calculate this Langevin coefficient, and this is their numerical data. Okay, so you can see that it looks kind of a linear growth in n. Okay, so they present this as a numerical support of their claim. But okay, so this is also for their numerical data for this Ising spin chain with the transverse field, and also with the longitudinal field. Okay, and this is their result. But okay, let's focus on this data. And this is a one-dimensional system, but one-dimensional system, one should have this logarithmic correction, but their analysis is kind of a qualitative analysis. So they just it looks like a linear growth, but they cannot. This is a quote from their paper. The logarithmic corrections are not clearly visible in the numerical data. So actually, actually, this logarithmic correction is always difficult to pinpoint. Okay, so, but I mean, this is a current situation of the numerical result. Okay, so up to now, I gave some review of existing theory, mostly, I mean, proposed by this Parker et al. In this paper. Okay. So now I decided to do some more extensive and thorough numerical study of this operator growth dynamics using the simplest model case. So I took this transverse field Ising spin chain. So this is the Hamiltonian. I mean, this is a one-dimensional system, and this is the. So up to now, this term and oh, I'm sorry, this must be Z. I'm sorry. So this is the Ising chain, classical Ising chain, and this is the transverse field, the Ising model. So up to here, this model is known to be solvable. Okay, so actually this can be explicitly solvable using the mapping to the free-formian system. Okay, but if you add this additional longitudinal field, and then this longitudinal field breaks the integrability, and the system is known to be thermalized. Okay, so ETH test of this full system was done in this paper, and this paper clearly shows that this additional longitudinal field breaks the integrability, and the system satisfies the ETH. Okay. Okay, so in order to study the operator growth of this Hamiltonian, so first I need to introduce the basis state, natural basis state for the operator. Okay, this is the natural basis state. This is a so-called Pauli string. Every site I have an identity operator or Pauli matrix. Okay, so this is a product state of this Pauli matrix. Okay, then any operator can be written as a linear combination of these Pauli strings, and of course this is a state in the very extremely high dimensional Hilbert space, because every site there are 4 different operators. So actually this is a linear combination of 4 to the L Pauli strings. Okay. So it's a very high dimensional quantity. Okay, so here I present some very nice property of this Pauli matrices. So the product of 2 Pauli matrices is equal to identity operator when they are the same. This is very trivial. The square of Pauli matrix is just the identity matrix. But if A and B is not equal to each other, then we should have another Pauli matrix. So this epsilon is the Levi-Civita symbol. Okay, and another interesting important property is that the Pauli matrix is traceless. If you take a trace, then it automatically vanishes for every XYZ Pauli matrix. Okay, so using this property, one can easily show that the product of inner product of 2 Pauli strings is non-zero only when these 2 Pauli strings are the same. Okay, otherwise, because of the traceless property of the Pauli matrix, this vanishes, the inner product. So every different Pauli strings are orthogonal to each other. Okay. And then what about the product of these 2 Pauli strings? Okay, the product of these Pauli strings, sometimes you have this identity operator, and sometimes you have this another Pauli operator, depending on the equality of 2 components. And because of anti-symmetric property of the product of Pauli matrix, you can easily show that this is strictly proportional to the product of 2 Pauli strings with the inverted order. Okay, and there is some phase vector depending on these 2 Pauli strings. Okay, so the product of tau tau prime and tau prime tau is equal to each other, or there is one minus sign. Okay, so because of this simple property, that the commutator of these 2 Pauli string is just given by the product times 2 or 0. Okay, so this is a very simple property. So using this property, one can access this operator dynamics very conveniently in numerics. Okay, so actually some numerical technique or some more additional algebraic property of this Pauli string can be found in this paper. So, using this property, I did some numerical study of. I can calculate this Langevin coefficient. Okay, so first I just want to show the Langevin coefficient for the integrable case. I have only a transverse field, okay, no longitudinal field. Okay. So in this case, I consider 2 different kinds of operator. One is the one-body operator, the Pauli matrix at the origin. Okay, or I also studied 2-body operator, Pauli operator at the center and the neighboring side. Okay, and these curves show the Langevin coefficient for these five operators. So if you look at this this data, then you will see that this sigma x operator belongs to the type 1. They belong to the type 1 category. Okay, the Langevin coefficient converts to a constant. Okay, and but if you look at this Pauli matrix in the z direction, this is the data for sigma z. Okay, and you can see this some curvature. Okay, so this curvature means that this is not this is a sublinear growth. So in this plot, in this panel, I plot the same data, but with the data against the square root of n. Okay, square root of n, and then you can see that this green data is just perfectly described by this square root, shows this square root of n growth. Okay, so this means that in the integral case, depending on the operator, some operator belongs to the type 1 category and some operator in the type 2 category. Okay. And here I do not show the data for the two-body operator with 2 sigma z, but because this transverse field Ising model has some symmetry, so actually this z is equal to the, if I remember correctly, this is identical to this operator. So I do not show the data of ZZ. Okay, then let's see what happens. Okay.
Yeah, sorry, just a simple question. This has been obtained, in the thermodynamic limit or for what?
Yes,
for
every calculation is in the thermodynamic limit. So I imagine some infinite one-dimensional lattice, and I start from the local operator at the origin. Okay, so actually all the information in the infinity doesn't matter because I am looking at the time evolution of this local operator. Okay,
I see. Yeah, correct.
So, but if you apply the Lagrangian operator, then I need to take care of more and more, lattice site as the support of the operator grows. Okay,
I see.
So every time,
and you can go up to 60 more or less. I see. Okay, got it.
So here, this is the integrable case so the growth of the growth in the operator space is not so dramatic. So I can go further, but I just stop here because there's nothing interesting beyond this. Okay.
Okay.
So that's a good question. So for the ETH case, we have to work only on the finite size system because we need to diagonalize the Hamiltonian. Okay, so every calculation should be on the finite system, but in this operator growth case, one starts with the infinite lattice, so there is no finite size effect. Of course, there is a finite n effect. Okay, then now I turn on the longitudinal field, but first I turn on the uniform longitudinal field. Okay, uniform means the strength of the longitudinal field is identical everywhere. Okay, so this black line means the field strength is 0. So this is just nothing but the transverse field Ising model case. So here I show the data from the sigma z operator. Okay. So this is the integral case, and now I turn on this longitudinal field slightly. So for example, the field strength is 10 to the minus 5 for this color, and 10 to the minus 4, 10 to the minus 3, and so on. Okay, so every data set, there is a tenfold difference for the strength, the amplitude of this longitudinal field. Okay. So first, just forget about this intermediate case, but just to look at this this case where I have an order 1 longitudinal field. Okay. So as you can see, there is some slight downward curvature. Okay. So then we need to say whether this downward curvature is coming from the square root of n scaling or logarithmic correction. Okay. So in order to determine the nature of this growth, here I plot in this combination. So instead of Bn, I plot n over Bn. The reason is that if this Bn follows this the linear growth with logarithmic correction, okay, then this means that n over Bn should be proportional to the log of n. Okay, so if I plot n over Bn with respect to log n, then if there is a straight line, then that means that is the conformation of this scaling law. Okay, so I plot n over Bn with respect to the Lambert W function here. Why instead of log n? Because the proof of Parker involved this Lambert W function explicitly instead of this log n. So, but actually, if you plot log n instead of Lambert W function, actually the conclusion is the same. But, okay. Anyway, so you can see that this data give this perfect straight line. Okay, so this means that this downward curvature is coming from the logarithmic correction. Okay, so this is a direct numerical confirmation of this hypothesis for the one-dimensional chaotic system. And then what about this intermediate value? Okay, so for the intermediate value case, for when G is very small, in the beginning they follow they seem to follow this integrable curve, type 1 curve, and then at some point they begin to deviate, and then they cross over to the chaotic scaling. Okay, and this crossover is also seen from this type of plot. So here they follow this, integrable curve and then deviate from it, and then they develop this straight line here. Okay, so this curve shows that at least in this regime, all the data is described by this n over log n scaling behavior. Okay, this is a numerical confirmation of the hypothesis. And okay, so for large n, I can say that I can reproduce this hypothesis. Then what about this crossover that happens for small n? Okay, so in order to analyze the crossover at small n, actually I found that so when G is small, they initially seems to follow this integrable curve here, but actually they begin to deviate from this integrable curve. Actually, so I decided to measure the relative deviation from the integrable curve here. Okay, so delta Bn is the deviation from the integrable curve. Okay, and interestingly, this deviation is proportional to the G squared. G is the longitudinal field strength. Okay, so because G is too small, I can see the difference here. But if I plot the deviation multiplied by G minus 2, and then what I found is that all the data follow the same universal curve here. Okay, so here they follow this universal curve. It seems like to be an exponential curve. And then at some point they deviate from this curve and then crosses over to the chaotic behavior. Okay, chaotic behavior cross over here. And because this universal curve has an exponential form, and actually this crossover scale, which is denoted by NCG, is proportional to the log of G. Okay, so every data has a tenfold difference of G, but this crossover point is equidistant. Okay, this means that actually this data already suggests that this crossover scale should be proportional to log of G, and actually this is confirmed from this crossover curve. Okay, so this red curve is some kind of master curve. So this is denoted by this scaling function. So this is the crossover. And then why we have this kind of crossover? Okay, so the crossover means this is the depth index of a Krylov space N. So there, when I have a integrability breaking field G, then there is some crossover scale N sub C. And below N sub C, the system behaves as in the integrable case, non-chaotic system. And beyond this, the system behaves as in the chaotic regime. Okay, so here the system behaves as in the non-thermal system, but the deviation has the deviation is proportional to the G squared. Okay, so actually this crossover, has the origin at the prethermalization dynamics. Okay, actually the prethermalization means that when an integrable system is perturbed with an integrating field, and actually the system behaves as in the integrable system in the beginning. And then the system crosses over to the integrable system. Actually, this kind of phenomenon has been reported a few years ago by many authors. And actually, these people show that the rate, the so-called prethermalization rate, this is nothing but a detaching rate from the non-thermal behavior to the thermal behavior. Using some perturbative argument, they show that this prethermalization rate should be proportional to the G squared. Okay, actually, this G squared is this means that the prethermalization rate is proportional to the. This is nothing but this prethermalization rate predicted by other people. Okay. So in that sense, this effect can be expected from the previous result. But what I still do not understand is that what is the role of this crossover scale? This is proportional to the log of G, but still I do not understand the role of this crossover scale in the context of prethermalization. Okay, so naively, one can think there may be two time scale. One is determined by this prethermalization rate. Another one is the time scale. Where when the system reaches this crossover scale. But so I think I need to study more. I need to do some quantitative study of this prethermalization dynamics to understand the role of this crossover scale. This is an open question. And I also do the same analysis for another operator, but So basically, I have the same result, but in this case, the crossover is more complex. So I think that the message is already clear here. So I just skip this analysis for the another operator. And then I move to the last part. So what happens when you apply some local perturbation? And actually, some people ask this kind of questions. I have an integrable system. And of course, if you apply some uniform integrability breaking perturbation, then the system eventually thermalizes. But what happens if you break the integrability with a local perturbation, not the uniform perturbation? For example, I have a transverse field Ising spin chain, but I apply only the longitudinal field at a single site, not the uniform field. Okay, or you can say that you can ask, I have an integral XXG spin chain. This can be, this chain becomes non-integrable if you introduce next to nearest neighbor interaction. But what happens if you turn on the next to nearest neighbor interaction only a single bond? Okay, so this is a very interesting question, and actually these people study this. The effect of local perturbation in the XXG chain. They did some really careful quantitative analysis using the so-called fidelity susceptibility, and they show that the threshold. So when you apply this local perturbation, then when the strength of the local perturbation is very small, then the system behaves as in the non-thermal system. But if you apply the strong local perturbation, the system behaves as in the thermal system. So you can define some threshold, system size dependent threshold, and they show that this system size dependent threshold vanishes in the thermodynamic limit. Okay, so that means in the thermodynamic limit, this the system should be eventually thermalized at any finite value of local perturbation. Okay, and actually Santos et al. Also claim the same conclusion for the transverse field Ising model with local longitudinal field, but their analysis is quite qualitative, not the quantitative. Okay, so I did some quantitative analysis for this transverse field Ising chain. Okay, so I decided to apply the local longitudinal field at a single site here. I applied this local field only at the origin. Okay, so here this means the no longitudinal field. So this is just a type 1 behavior. But if I turn on this local field, then I also have this crossover behavior, which looks very similar to the crossover in the previous case. But actually, the scaling behavior in this region is not the type 3 one, not the chaotic one, but so if I plot this data with respect to the square root of n, then I have a perfect straight line. Okay, this means that then what about this this type of analysis? If I plot the data in this way, n over bn with respect to the log n or Lambert W function, if this data follows the type 3 chaotic scaling, then I should have the straight line here. But as you can see here, there is a persistent curvature in the data. Okay, so this means that if I turn on the small local field, then there is a crossover, but this crossover is from type 1 to type 2. They still in the integrable, the non-chaotic regime. Okay, so this data means that if there is a non-thermal to thermal transition in the transverse field Ising chain with a local perturbation, then the threshold should be finite. Okay, this local field strength should be large enough to induce the quantum chaos. That's my conclusion. So,
but Jae Dong, question.
Yes.
But suppose that you go to large n. I mean, when I say n, I mean small n. Do you think that these deviations from the, let's say, type 1 will be? I'm wondering if at very large n you will get finally the type 3 case. So you have, let's say,
if I go beyond 16, for example, if I go to 100, something like that.
Right. I'm wondering if you will see, let's say, a type 2, let's say, crossover behavior, and then finally you will have type 3 or not. What do you expect? Because Pandey et al., they claim that, right? I mean, they claim, okay, this model will thermalize, but in very long times. So that means in this language at very large n. So I was wondering if you have an expectation or you cannot say anything.
With my data, I cannot say. I cannot disprove your claim. So,
but your feeling is that you will never reach a type 3. I mean, I'm asking you to bet. I'm not asking anything.
So one thing is that this is for the infinite system size. So if there is a really crossover in the really large n, then there should be some reason for that. Okay. But I do not have any. I cannot imagine any special reason for that. And actually, here this is a numerical data of Santos, and for XXG chain case, they really perform the quantitative analysis for the movement.
Right.
Okay. But in this case, my feeling is that this is just a qualitative picture.
Right.
So I think,
I'm more familiar with the Pandey et al. Analysis. So
this one. Okay.
Yeah. There, I remember that they were saying, well, I mean, even an infinitesimal perturbation will be enough to thermalize, but you have to wait for very, very long times. But now your data instead tend to say maybe not. So yeah, I'm curious.
That's why that's why. I mean, this prethermalization rate is proportional to the G squared. So when G is very small, then you need to wait long enough.
Right. I'm wondering if one can cook up a variation of SYK with a one-body term and do analytically to see this transition. I mean, because there you really have the analytical formula. If you turn on a one-body term, I mean a quadratic term, probably you can play a similar game in that setup.
So you mean that you have a SYK model with one-body hopping term?
Right.
And then you turn on the multi-body hopping term.
Or vice versa, let's say you have the multi-body, I mean the two-body term, and you turn on a very, very tiny amount of the single-body term, and maybe you can study analytically, let's say the relevant.
Yeah, sorry for interrupting, but I mean, you need an integrable system in my understanding. You don't want to start with a chaotic system and...
Sorry. No, Jae Dong is right. So you should start with the integrable case with with the single body term, and then turn on. Yeah, absolutely. Sorry.
Yeah, sorry, but then since I already interrupted, can I ask a question? I mean, basically both of you. So here you consider the 1D model. Is that really relevant? I mean, I think there are integrable models, say something like Richardson model, which I think is all-to-all, and that is integrable. So you perhaps could try perturbing that one and trying to see what will happen. I'm not sure it will be solvable, but maybe things are a bit easier there.
I see.
Easier means in the analytic way or numerical way?
Yeah, I mean, basically, it's more like the hope that because the model itself is not only integrable, I mean, it's basically solvable for any single, you can tune the single particle spectrum at will, and it's always solvable. So basically, the hope is that maybe, if not completely solvable, even in presence of a single link perturbation, then maybe at least the analysis can be pushed to larger sizes, or yeah, something along these lines. I'm not at all sure. I'm just wondering whether, to answer this question, whether one might just try to look at kind of, let me call it integrable mean-field models.
Mean-field model.
I don't know. Yeah, on my side,
yeah, I mean,
I think
I can.
Good direction.
Yeah, I mean, I can only say that there could be a counter argument saying that first thing, this is not 1D, not even 2D. That's basically very high dimension, so things might just be different because of that. That's like the immediate counter argument I can think of.
Okay, so actually I have, this is my last page, so let's finish this formal one, then I think we can discuss further, okay? Okay, this is just a summary of my work, and what I learned from the study of transverse field Ising model is that this operator growth dynamics is extremely useful because it tells us something about this crossover. And this crossover is very, I mean, clearly shows the presence of prethermalization rate, and it has a very nice mathematical structure, at least for, I mean, signature of mathematical structure. Okay, and actually, I only show the result for the Ising spin chain, but I also did some numerics for the XXG chain. But it turns out that the XXG chain is the performance on this XXG chain is not so impressive, which means that XXG chain becomes non-integrable if we introduce the next nearest neighbor interaction. So the growth, spatial growth, I mean, is twice faster than the Ising chain. So I cannot go. I mean, in numerics, I can access only a limited depth in the Krylov space. So it's very hard to say something on. I mean, even I cannot sure. My numerical calculation do not show. I mean, it's very hard to say whether there is this logarithmic equation or not, even for a highly non-integrable case. So there's some limitation of this method. And also, Kao also shows that in some MBL systems, actually this is also the Ising spin chain with random interaction. He claims that he showed that even in this MBL case, the system follow this chaotic scaling. So actually, this must be, I mean, settled down. Okay, so MBL is believed to be non-thermal, but if their result is correct, then even though this system is not thermal, they also follow this maximal operator growth. So this must be settled down. Okay? And for my last hope is that actually this transverse field Ising model is maybe one of the simplest systems. So hopefully if one can solve analytically this operator growth dynamics using some combinatorial method, because one can formulate this operator growth in the combinatorial way. I mean, so this is my just hope. Okay, thank you so much. Okay, thank you.
Thank you, Professor Noh, for your excellent talk. Let us thank our speaker.
And there is a
question. Yes, Alexei, please.
Yeah, thanks. So this time I asked the question officially. So I just wanted to make, well, I have several questions, but my first comment is about the operator growth in MBL systems. Wouldn't it be immediate? I mean, the fact that the growth of these operators seems to be thermal, could it be related to the fact that it seems that different measures basically give different position for the MBL transition? Could it be they were just, well, this is yet another reflection of that? I mean, there was a debate recently whether the MBL phase exists at all, and I think there were studies, well, at least one study I'm familiar with, showing that depending on which measure you take, like the ratio of adjacent gaps or others, you get different position of the MBL transition. So then, could it be that this thermal growth of operators that Kao observed was related to that they simply didn't went deep enough into the MBL phase?
Okay, so you mean that the thermalization of MBL system may depend on the choice of observability? That's the...
Now, more like, I mean, most studies were done numerically. So of course, if you can go in the thermodynamic limit by a miracle, I guess I mean, there's either a true transition and then all the measures should give the same result, or there's no transition. But what I'm trying to say is rather that because we can only access finite system sizes, there might be strong finite size effects. And actually, there seem to be strong finite size effects.
At least for the work of Kao, actually, his argument is based on some symmetry property of the operator, which is which does not suffer from finite size effect. So actually, some very specific property of the transverse field using spin chain. So
okay.
So actually, he also mentioned that there are some debate on the thermalization is the issue of the MBL system. But so that's all I can say so up to now. So actually, this is not kind of obvious question.
Okay, thanks.
Do we have further questions? So let me ask maybe, so you've shown 3 exactly solved cases, right, for the effective tight binding model. So the types 1, 2, and 3. So is this all there is? I mean, I guess the types 1 and 3 are kind of the limiting cases in a sense. So free model and kind of maximally chaotic. Could there be anything else, or are there any other analytical solutions for these that are just maybe not relevant for the question at hand?
So actually, if you assume that Bn is proportional to the n raised by some power delta, for example, okay? Then you can solve this discrete Schrödinger equation, and to find you can obtain some scaling law of this. But as far as I know, actually, these three cases are realized in some microscopic model. For example, Ising chain and XXG chain and SYK model. But I do not know. I mean, another example which outside of these three known cases. But of course, actually, as you can see here, this Ising case, you have some small oscillations. Okay, so so basically, if it is strictly constant alpha, then this is the exact result. And if you have some oscillatory correction here, then the form is different. For example, this small oscillation introduces additional power correction to the correlation points, but they do not modify this the growth of in the average kilo depth. So as far as I know, these three cases are the known case where, I mean, there are some definite microscopic correspondence. I do not know any other examples.
Okay, thank you. Alexei, do you have any further questions? There is still raised hand.
Yeah, actually, I have a question, but a very simple one that's related to taking the transverse field Ising model and just adding perturbation that breaks integrability on a single side. Would it be of any help to go into the free fermion representation? So basically, is this of any help in analyzing the effect of the perturbation?
So your proposal is, first I transform the Hamiltonian to the free fermion version.
Yeah.
And then apply the perturbation.
No. My suggestion is exactly you take the transverse field Ising model, you consider the same perturbation. Well, you add the perturbation and then you do the transformation. I guess you end up with a model where now the perturbation is no longer local. And that's precisely why I'm curious whether it could be of any help. I mean, looking into the fermionic picture rather than the spin one.
I mean that I first go to the free fermion model and then apply the perturbation on it. That's your proposal.
No, the opposite. Start with the transverse field Ising model, add the perturbation, and then do the Jordan-Wigner.
Okay. So this local perturbation introduced the coupling to sigma z, right? Sigma z. Sigma z in the Wigner-Jordan transformation becomes a string operator, isn't it? Not the local one.
That's why I'm asking. I mean, my expectation is that if you do that, you'll end up with a model where you would have a non-local. The Hamiltonian will contain a non-local term. And I'm then curious whether that alone might be helpful in understanding how operators would spread.
Yes, so in the numerical sense, it becomes much more difficult, but maybe one can get some analytic idea.
Okay.
Yeah, I think one can try. One can try that way, but I cannot say anything.
Well, that's what I mean. That's why I was asking. I was whether there's like any immediate argument. Okay. Yeah. Thanks.
Do you see some, the shape of the curves that you report here looks very similar, both in the shape but also in the meaning somehow, with the scaling of the adiabatic gauge potential of Pandey et al. I remember that they suggested that there might be a connection between the adiabatic gauge potential as a function of n and the Bn in the thermodynamic limit, but they don't say anything. Do you have some clue about that, or have you think about that, or?
I mean, you mean the connection of this fidelity susceptibility? I mean, to this.
Yeah, I mean, they talk about this. They essentially as a measure for chaos, they take the scaling of, let's say, of the norm of the adiabatic gauge potential with n, with the system size. And they see they at the end find curves which are extremely similar to the curve that you draw in the next slide, in which you have, for example, I mean, a departure from for example, from this as and also in your case as a function of n. Of course, the two n are different, but in your method somehow this n is a sort of an effective dimension of the system, right? Because you say, okay, I'm in the thermodynamic limit, but exactly because I'm in the thermodynamic limit, only a length of length n is relevant. So I was wondering if the two things have they also mentioned there might be relations, but they don't say anything more than that. I was wondering if you thought about that or not.
No, I didn't think in that way. But actually, here their conclusion is based on the finite size scaling, the kind of the scaling of the effective transition point as a function of the system size.
Right.
But here, this crossover just this is basically I am in the infinite system size, and this crossover give us some information on the dynamics.
Yeah, that's right.
For shorter time, it behaves as non-thermal, and in the late time.
Yeah, that's right.
So,
Right. Okay.
Maybe if we can relate the crossover time scale here and the crossover time scale here. I think that
because again, okay, maybe I can recast the question in a different way. Can you understand the behavior of the BNs in terms of ETH or not? Not directly.
BN in terms of what?
Of ETH, of eigenstate thermalization hypothesis. I mean,
ETH? No. I have no idea.
Okay, because essentially their curves for the adiabatic gauge potential are motivated by eigenstate thermalization hypothesis. So if a connection should be there, probably the connection should be like an understanding in terms of eigenstate thermalization hypothesis of the Krylov coefficients, but it's not for the moment, right?
No. But that's also a good suggestion. The connection of ETH and this operator growth dynamics, that's also a good direction. I mean.
Yeah, it looks that Alexei has another comment, right?
No, I think it's just the hand didn't go. I mean, yeah.
I see. Okay.
Okay, so do we have any further questions from the audience? It seems not. So in this case, let us thank our speaker again.
Thank you very much. I'm sorry, because I overspent the time.
It is okay. So yes, with this we conclude our seminar. Thank you all for your participation, and see you